And many of you, I think, will also be there for our evening sky viewing program, which starts a little later, of course, after it gets dark. And that will happen, as you know, in the Science Park area. And there have been passes, etc., given out for it. Every year, we, as part of the National Science Day, we have one or two talks on, typically one talk, on the Physics Nobel Prize given that year. And it actually happens at the end of February, and the Physics Prize is announced in October, given in December. So people have, by this time, often forgotten about what it is all about. But just to remind you, this year, the Physics Prize was given to astrophysics, and in two different areas. And that is why this year we have two different talks talking about cosmology today and extrasolar planets, discovery of extrasolar planets. And that talk will happen at the same time tomorrow. This year it's my immense pleasure to welcome Professor Tarun Souradeep, who is currently the chair of physics at IISER Pune, our neighboring institute. He is, of course, has been in IUCAA from the very beginning. He was a member of the first batch of PhD students at IUCAA. And he was one of the earliest PhDs that IUCAA produced, and then he went off into the world to do his postdoctoral routine in Canada, for example, at CETA in Toronto, and then in the US, and then came back to IUCAA as faculty, and only recently has he gone on deputation to IISER as professor and chair of physics at IISER Pune. In fact, this probably is his first time giving a talk. He's given many talks in this auditorium, but giving a talk, coming back from his new job in IISER, coming back to IUCAA, and welcome him back. Very nice to see him here. And of course, please stay on after the talk. There will be questions, and we'll be happy to answer them. The talk talks about Jim Peebles' role also in, of course, Jim Peebles, who got the Nobel Prize for cosmology. And I must tell you that Jim Peebles has visited IUCAA on various occasions, and many of the people here have interacted with him all over the world. And I hope Tarun will talk about his interactions with Jim as well. Tarun.
Good evening. It's, of course, a great pleasure to be here, and I must begin by thanking Director IUCAA, Shomak Rajadhiri, and my young cosmology colleague, Surud More, for inviting me here. I just did that so that I don't forget to do so, because I'm not used to being invited here yet. I mean, I'll probably get used to it. So today, I am particularly pleased that I'm going to talk about a subject that has been dear to my heart. I mean, this is something, an area that I've worked in right from my PhD days, and I've seen this story unfold as to how, human beings on this tiny planet Earth figured out the workings of the cosmos. And we are here to celebrate the Nobel Prize that was given to Jim Peebles, who was one of the many scientists around the globe who helped unravel the mysteries of the universe. But his story is kind of interesting and unique, and I hope I'll be able to convey the basic gist of what how big his contribution has been and where it has been. So before I begin, I mean, since in this, our day-to-day humdrum, you see a lot of things happening which are pretty, you look at planet Earth, things are not very pleasant. So I'd invite you once in a while to look at pictures like this, which tells you, there's absolutely splendid cosmos all around us to look at and enjoy. And that might relax you. This is a picture by one of our astronomer colleagues who works at the High Altitude Observatory in Hanley, Dorje Angchuk. And he has beautiful pictures of this kind. So I really want to tell you to go and really look at the album of amazing pictures of the sky. And I'm sure young kids like one sitting here will get excited about astronomy just by looking at such pictures. So let's, let me just see if the transition thing works, yeah. Oh. Sorry about that. Yeah, okay, so this time I was really appreciative of how the Nobel Prize committee kind of brought together two relatively disparate areas but frontiers of astronomy into one single title, Our Place in the Universe. And in some sense it really captures the work that was felicitated by this Nobel Prize. This half was given to Jim Peebles, whom I'll talk about. The other half went to these two gentlemen, and I won't really say anything about it except for meeting Shomuk's invitation for you to come tomorrow and learn about this half of the Nobel Prize on extraterrestrial life. Okay, moving on to Jim Peebles. Do you know why this is not working? Is it turned on? Yeah. No, laser pointer is working, but the transition is probably not working. Okay, fine. I can use this. Okay. So here's Jim Peebles. The Nobel Prize citation says he's being given the Nobel Prize for a new understanding of the universe's structure and history. And that's very apt. And I would try to capture his work or style of work or what he did for cosmology in this quote that he himself made in 1988 in an interview. He said, and if you had read the abstract of my talk, very similar, and I was quite pleased to see that, the universe is simple. It's expanding in a computable way, which is an amazing thing. I would have never anticipated it could have worked out so easily, but there it is. So the universe is actually, on the whole, a very simple system if you really look at it. And you can work out in detail what you should expect to see in the universe. And what is amazing, I hope to convey by the end of the talk, is just using basic physics, what we have uncovered and what kind of exotic phenomena well beyond whatever we have seen in our laboratories exists, just because our cosmological observations tell you so. Before some of you get lost in my talk, I wanted to summarize what is Jim Peebles' contribution to cosmology and just try to capture it in one slide. So it's essentially studying the physics, studying basic physics in the context of the cosmos, in the cosmic arena. And when in the early 60s, when he started working as a PhD student, this was an area which wasn't really the most fashionable. Most people would have, advised students not to get into it because it was ill-defined. But he saw the charm of, a new, fresh area in which you could apply basic physics and try to uncover the truth about the universe. And that's what he did all through his career. So he actually developed a lot of the formalism and the observation language that we use. He with many others, but largely he pioneered the study of clustering of galaxies, fluctuations of the cosmic radiation I'll talk about. He also worked on nucleosynthesis, how primordial nuclei were created. Many such phenomena. I mean, his career, if I forgot to mention in the previous slide, it's a huge lifetime, 58 years, absolutely working at frontiers of cosmology. Almost every few years, he has produced very interesting work at the frontiers of cosmology. And he still continues to, challenge his own model. So that's one. Another aspect is physicists do not like the idea of things happening by chance. We don't like things to be, you don't want to say, oh, it happens because it is so. Or it happens, the ball is falling because it happens to fall. We know that it's a force of gravity. We want to calculate it. Similarly, about the universe, when you find things which seem to be happening without any apparent reason, it can only happen in a very fine-tuned situation. As physicists, we feel awkward, and he, being actually a physicist at heart, pointed these out, and they, as I'll point out later in my talk, spurred others into hunting for ways out of it. And I think that was another very, very important aspect to his style of work. Okay? And broadly, what he did was, very sincere work of looking at a model, looking at what you think is the cosmology now, and work out things that can observe to now sort of pit it against observations, pit your model against observations, whatever is there, try to see if I can take my theory of the universe and not just be happy, oh, it's a beautiful theory, or oh my God, how lovely it would be. But he says, okay, now let me compute something in it and match it to observations. And he did that all through. And even now, to this date, I believe his attempt is always to look at observations and try to see if they are challenging the theory. And in doing so, what was interesting, I think he sort of proposed, as you found that your current understanding of cosmology didn't quite match with observations, he was bold enough and also convincing enough to tell the whole community, hey guys, let's look at this workaround. It seems to be good. And this is amazing. And he's been right in the current context many, many times, certainly 2 major times. He proposed that there would be dark matter dominating over ordinary matter that we are made up of in the universe. On the cosmic scales, he said the cosmology is such that cold dark matter, I won't get into the cold part of it, you can ask me the question, but dark means it doesn't interact with electromagnetic light, and matter is, we call it matter because it clusters under gravity. So, these are ways of just conveying that idea. And that he did in 1980, as I'll point out, and I'll try to tell you how he came to that conclusion later part. But this is one important contribution. And then about 2 years later, he also came to the conclusion that not only there has to be cold dark matter, but you cannot do without introducing something like a cosmological constant. Now, many of you would have heard in kind of the lore, I mean, it's probably true, I don't know, or not true, that Einstein proposed something called a cosmological constant, which was consistent with his theory of gravitation. It's allowed in his theory of gravitation. And he used it to propose the first model of cosmology, but later when he found an expanding universe, he was trying to keep the universe from expanding. When the universe was found to be expanding, he threw it away. And he resurrected the cosmological constant to be the dominant energy density in the universe, which dominates even over the cold dark matter. And cold dark matter dominates over the ordinary matter. So we are led to a very exotic model of cosmology, which I'll talk about. The current lambda, which refers to this cosmological constant, and the CDM refers to this cold dark matter, standard model of cosmology, is something that came out of his work. He was the first one to say these two must be in the cosmological model. These two elements have to be there. Exotic, but true. And, as I'll tell you, he was spectacularly right. And just to point to the fact that not only did he work like this, he also conveyed it to a generation of physicists who were brought up, and astrophysicists and cosmologists who were brought up on his famous books. So this is a book written in 71. You see the title of the book, Physical Cosmology. So he looked at cosmology as an arena in which you do physics. He looked at it like a physics system that deserves to be studied by physicists. And then Principles of Physical Cosmology in 1993. And so in that sense, he is a father figure in the field, where most people that you would see now, even very famous cosmologists of this decade, of this generation, and have gone and learned cosmology from these books. Okay, so now what do I mean by studying physics in the cosmological arena of, cosmic arena, right? And so I have to explain to you what is the cosmic arena. And let's look at this picture again. Again, one of these beautiful pictures you should look at whenever you're sick of things happening on Earth. And if you look at the sky, here's the Milky Way, is beautifully reflected in the lake. And Milky Way, whatever you see in this picture, are largely stars that are just around us in our own galaxy. But suppose I was to choose a dark spot well away from this plane of the Milky Way. Okay, here, since I can't go far enough, I'll choose it somewhere here and zoom into it with the most powerful telescopes you have. So the Hubble Space Telescope, I'm sure everyone has heard about, stared at a part of the sky and produced what are called ultra deep fields, and Hubble Deep Field and ultra deep field. And if you look at this tiny patch of the sky, okay, it's full of galaxies. So we realize that our galaxy is just one of billions of galaxies out there, right? So it's a very rich, cosmic arena that we are inherited. Okay, and let me just remind you what a galaxy is. So for the rest of the talk, this entire galaxy, which is itself, light takes about 300,000 years to go across a galaxy. Light takes that much time, right? And this is a galaxy, huge system in itself, worth a lifetime of studies by many people. We had 100 billion stars, and each star weighs about 10 followed by 30 zeros, okay, in kilograms. So this is a massive entity itself. But on cosmic scales, this is just a speck of dust. The way we look at the cosmos, since there are billions of such galaxies, it's like trying to study the air in this room. So you don't worry about the chemical composition of every dust particle. For them, they're just particles around, right? You don't worry about this. That's how we will be treating galaxies. Now, if you look at galaxies in that frame, you realize that there's something very interesting in our universe. If you look at the universe around us, so we are at the center, and you are sort of making a map of where galaxies are in the universe around you. And you see that there's a very, very rich structure emerging. Galaxies are not uniformly distributed around us. They're, in this cloudy structure. Each dot in this cloud is a galaxy. One of these small clouds is a cluster of 1,000 to few thousand galaxies, right? These are clusters and superclusters. And this is, again, just our local neighborhood. Even if we go here, now light has started taking 100 million years to go this distance. So across this picture, it will take, 1,000 million years, a billion years to go across this. Now let me zoom out and show you how the cosmos looks now, right? We know that it's full of galaxies, and this is, kind of spread in a very cellular structure here. And what you were seeing around us as a galaxy is just a zoom into this. So this is, just to start so it's a flyby through the distribution of galaxies. So any part of the universe you go through, you will see the galaxies all around you, and they're all organized in some very, very filamentary, structure. It looks like as if you're looking at a sponge, right? And the galaxy is sitting at the place where the material of the sponge is, and there are the gaps and huge voids in between. And these are each individual galaxies. So you can see in this whole thing, not only our Earth is a speck of dust within our own galaxy, our galaxy itself is a speck of dust in this whole cosmic arena, right? And imagine the audacity of saying that, okay, we will deal with it with the physics that we learned in our laboratory and try to make sense of it. And this is the kind of, bold assertion and conviction that the cosmologists in the previous generation had. And they went ahead with it. So now whenever you are, if you look at this picture, of course it looks mind-boggling. How do I ever get hold of this into something that is tractable as a problem in physics? You want to pose it in a solvable way. So one thing that, again, I'm borrowing a picture right out of one of the textbooks that I showed you of Peebles, James Peebles. He points out why there is simplicity in the cosmos. So you have this amazing structure in the distribution of galaxies. But if you were to project all of them back to the sky, you don't care how far they are, but where they are on the sky. Even in the 70s, the Lick Observatory Survey, whose picture is in his book, already convinced him that no part of the sky looked particularly different. Okay, of course, a part of the sky is cut out because our own galaxy runs through it. But if you look at it, there is some graininess, there is some patchiness, but no particular direction is crying out and saying, oh, I'm a special direction, look, I have so many galaxies, or I'm completely devoid of galaxies. Nothing like that. So it's fair to assume, at the first approximation, that the distribution of galaxies around us is on the average, in any direction, we have the same number of galaxies. So there's an isotropic, we use the word isotropy to say something is the same in all directions. So if the distribution of galaxies is isotropic around us, and we are humble enough to accept that our galaxy is not special, and I'm sure the pictures that I showed you would have convinced you that we are not likely to be anything special. You take this, and it's a mathematical fact that a universe where the mass distribution around any galaxy is isotropic has to be a homogeneous distribution of galaxies. So on the average, the distribution of galaxies is homogeneous in the universe. So matter is homogeneously distributed, which immediately allows you to, attack the problem in a tractable form. You know that Einstein's theory of gravitation is this theory of gravitation. You use it. On the right-hand side is the matter content, and you use the simplest form of matter content, uniform matter content. And that itself led to the first surprise in cosmology. Okay, so much so that Einstein had difficulty accepting it. So Einstein's general relativity applied to a uniform distribution of matter on cosmic scales leads to a smooth expanding universe. It could be also a contracting universe, but later it was seen that we have the expanding solution which matches our cosmos. And this is amazing, right? It's just so amazing that someone who brought in relativity and ushered in quite a bit of quantum mechanics, very revolutionary ideas, himself could not accept that the universe you are in is dynamic. It is expanding in time. So what do you mean by dynamic and expanding in time? If I had a uniform distribution of points in the universe, which are galaxies, then at every place, every galaxy is moving away from the other. It's as if these galaxies are spots on a membrane that is magically stretching. And the space between the dots is increasing. So there's space being created between galaxies, and the universe, the spatial part of the universe, is expanding. This is the view you should have. And that immediately also explains for you Hubble's discovery that for any galaxy, every other galaxy appears to be moving away from it, which was his deduction. So in this model, the simplicity of the model is extremely appealing. It also makes it tractable. So now in cosmology, if I want to understand the universe, I have to only worry about one thing. How much was the expansion between time 1 to time 2? Right? How did the universe expand? And you can write down the equations, and it turns out to be just an algebraic equation. Okay, you take every kind of matter that you can conceive of in the universe, talk about it in terms of something called the characteristic density of the universe. It's also called the critical density. It's actually called the critical density, which is related to the expansion rate. Then all of these should add up to 1. Okay, and so if you have different values of those now, you will be on a universe on one of these tracks. Now once you have determined which track you are on, at one go, sitting here, once I have figured this out, I can tell you what the universe has done in the past up to very, very early times with immense confidence, with physics that is tested in the laboratory, and also predict for you what the universe will do in the future. Okay, And that whole power comes from the power of simplicity. We have a simple model of cosmology. The universe lends itself to a simple model. Okay, and that's something that I think Jim Peebles realized and pushed very hard. So for example, now how do we know that the universe is expanding? We know the universe is expanding because if I work out in an expanding universe, what happens? So there are interesting things that happen in a universe, expanding universe. We are not used to it. The universe here is not expanding. Our lab, when we do experiments, the lab apparatus, is not in an expanding universe. So we are not used to it. So you have to get used to the intuition. So some of the intuitions you have to build up. And so one of the things that happens is everywhere, if I have an atomic clock here and another one in a distant galaxy very far away, atomic clock would click at the same rate, right? Atomic clocks are supposed to be extremely stable. Now imagine this clock sending out signals to us, right, at every regular interval of time. Okay, tick here. Notice that in the way I have drawn the world line of these galaxies, okay, the light from this signal comes exactly along parallel lines like this, and one tick here would correspond to 2 ticks of the clock and my thing. So that means this clock appears to be running much slower than this clock, almost half the speed, right? So that means phenomena that you see in a distant galaxy, okay, appears time dilated. Something happens rapidly, but the signal that comes from it makes it, if you time it using those signals, you'll find that the same event has taken a lot more time on your clock. This is just a simple thing that comes out of doing your simple physics, not geometry in an expanding universe, right? And that leads to the understanding of what Hubble saw. So what Hubble saw was light from a distant galaxy was redshifted. Now imagine what is light. Light is a wave that has a particular frequency, right? So there's a crest and another crest. So when I say there's the time period of light is this much, I'm measuring when did the first crest come and the second crest come. And what happens is just like this, events are getting time dilated, the time period is getting shifted, right? So you see the light to be redshifted, right? So you see that the frequency of light has gone down. There's another thing that happens in an expanding cosmos that you need to understand to appreciate what cosmology is all about. That's to do with what happens if a box expands. So if I have a number of galaxies in a part of the universe and I draw a box around it, say these galaxies. Now when the universe was half its size, okay, so the same number of galaxies are enclosed in the box, so the density would have gone up by a factor of 8. Okay, the size of the box has become half, and that means the volume has gone down by a factor of 8, density goes up by a factor of 8. When it goes to 1/4, it goes up by 64. That's easy to understand. Now imagine instead of galaxies, you have the same box filled with radiation. Okay, now when the universe was half its size, remember that clocks were appeared to run slower there for this guy, right? So that means this frequency here was higher than the frequency here. So not only the number of photons, the particles of light, are going down by 1 over L cubed like this. So that goes down by goes up by a factor of 8 here. But each particle of light has a higher frequency by a factor of 2. So the energy density of radiation goes up by a factor of 16 here. And here it's 128. So you can see if I go back like 1/8, 100th, 1000th, there will come a time when the energy density of radiation, even if it's much smaller now, we know that it's about a part in 10,000 of the energy density, MC square kind of conversion of the energy density in galaxy. This radiation would dominate the universe, right? So in an expanding universe, it's eminently clear if there are galaxies and if there is a cosmic radiation bath. In the past, in that expanding universe, there would be a time when the energy density of the cosmic radiation would overwhelm the energy density of normal galaxies. So for understanding the origin of the universe or early times of the universe, you can even neglect all the complexity that is there in galaxies and all, and worry about a universe full of radiation. Okay, so the early universe is always radiation dominated in the expanding universe. Now where is all this radiation? So people figured this out with the cosmological model by the 50s. Already they realized that there must be some signal of this hot early universe, right, when light, matter and radiation were in equilibrium. And this was discovered quite by chance in 1965 by Penzias and Wilson in testing out a new horn antenna, radio antenna that they had built. And they couldn't get rid of one noise and they kept trying. It seemed to come at all times from all directions. And a few kilometers away, in fact, Peebles' mentor, Bob Dickey, they were all looking for this radiation because they expected such a thing to happen. And by chance, it so happened there was communication between them, and Dickey told all these young people that we have been scooped. So someone has detected the radiation that we are looking for. So it's a serendipitous discovery, but already people were searching for it. So it would have happened sometime soon after that. It's amazing. This is the dominant radiation content of the universe. Although if you look at the temperature of this thermal bath of photons, it's only 3 Kelvin, just 3 degrees above absolute zero. Very cold, but it still accounts for almost all the radiation content of the universe, okay? And it's isotropic, okay, which is the strongest support for the model that I was building. I built it on the distribution of galaxies, but if the radiation itself is so smooth, it's a much stronger case for me to say that the universe is smooth on scales of, whatever the smoothness of this radiation is. And for 2.5 decades, this remained the case. We did not detect any fluctuation in this thing. So what we used to look at is this thing. So we were looking at the surface, which was 43 billion light years away. It is actually a glowing plasma surface. So the temperature at this surface is 3000 Kelvin, right? But the universe has expanded by a factor of 1000 from this time when it was 500,000 years old to now, and hence the energy of each photon has gone down by a factor of 1000, and the temperature has come down to 3 Kelvin. So the same radiation bath that is emanating from this plasma stream, okay, it worked at the wrong time. Surrounds us in all directions. So if you peer back into a universe, you will of course see galaxies far away. As you know, as I see a galaxy far away, or even when you look at the sun, you are seeing the sun as it was 8 minutes back, right, earlier. So you're always looking into the past as you peer deeper into the universe. So here, when I peer back and look at this microwave background, I'm looking at a universe which was only 500,000 years old compared to 14 billion years old universe now, right? So we are looking at a very early snapshot of the universe. And so let me skip this slide. Now this was the situation. So we had on the average smooth distribution of galaxies, and correspondingly, as far as we could see, a very smooth distribution of radiation all around us. The radiation content of the universe was smooth around us. What Peebles and his efforts and the whole group of people, cosmology driven by people like Peebles, brought in is the concept that we not only need to understand the smooth universe, but the fact that there is such clustering in the universe. So you looked at the perturbed cosmos, not just the smooth cosmos. And so if you look at a piece of this distribution of galaxies that I was showing you the video of, typically this is actual data from 2-degree field, which shows you a network of very rich organization of galaxies in the filaments. And you want to understand through basic physics how such clustering can happen, starting from small fluctuations that maybe have been there in the early universe. And so so for some time, of course, and this is where, again to point out, Peebles has even a textbook on this topic, like working out all manners in which you should study such distribution. Okay, the textbooks actually marks someone. It's typically you write a textbook when you've mastered a field, right? That's the trend most places. And then it tells you that he's a person who had mastered this field and ended up with this book which described how to look at the perturbed universe and galaxy distribution. He also was among the first to look at the fluctuations that would have been there in the background radiation. Okay? As I said, for 25 years, since 1965 to 1992, in fact, you did not see any fluctuations in this sky. But when you got to contrast levels of 10 parts per million, you started seeing that a microwave background was slightly hotter, slightly colder in different directions. So at the level of tens of microkelvin in this 3 Kelvin bath, right? And that was really an amazing point, transformative point in 92, when cosmology started, picking up steam in terms of understanding how the universe works in detail. That's one direction from which there's huge progress. So again, remind you, this is 500,000-year-old universe. It's like a plasma screen surrounding everywhere. I mean, you look at any direction, you're going to hit this. Okay? It will be 43 billion light years away. And there is the early universe being shown on it, a picture of the early universe being shown on it, right? And the challenge is to take this picture of the early universe where these fluctuations that you see in the radiation are signs that there were small fluctuations in the early universe, use basic physics of gravitation, how things cluster under force of gravity, and understand how this rich structure of galaxy distribution appears now. This has been the story that has, been followed. There's another aspect to it which I'll come to towards the end, last 2 slides, is you would at some point also ask the question, where did these fluctuations originate? But that's a story that is for the later. So let me focus on the part which again Peebles was one of the early people to work on, is what is the pattern of fluctuations that you see on this plasma screen. That's a particularly very simple concept. So I am looking at a plasma screen. Plasma screen is almost like a, surface of water on a lake, right? It is elastic in the sense that if you perturb it, it will try to restore itself. That's because, atoms are ionized and tightly coupled to radiation. So there is a restoring force of radiation which tries to keep matter from clumping up. And so it behaves like same way like a drum, right? So like a tabla. So imagine that surface that you have there is a tabla and someone has played on it. So you see the fluctuations on it. Now you have to read off the cosmological information from that, right? So how do you do it? So all of you in Pune are very familiar with music. So most of you have seen how a tabalchi knows whether the tabla has been tuned right. What does he do? He hits it with a hammer. Okay? We physicists also do that. We have a very fancy name for it called the green function. Right? So you take the plasma and hit it with a hammer and ask what happens. Right? You create a spike in it and ask what's the reaction. So what happens is the normal matter which is ionized, the normal atomic matter is ionized, it runs away in a ripple with the radiation, right? It's like a raindrop falling on the surface of a lake, right? So suppose I'm standing by a placid lake and there's a burst of shower. Everywhere a raindrop falls, a ripple will go out. After 10 minutes, if you look at it, you'll see choppy waters. But you should remember that everywhere a raindrop fell, there was a ring which went out, a particular distance and then stopped. And this distance can be calculated in cosmology. We know the speed of sound on the plasma, and we know how far this ring would have gone. So that is a marker for the fluctuations that we see there. And that in what is called a Fourier space in terms of wavelengths, gives you these kind of curves, a power spectrum. So even if you did not get the power spectrum part, remember that for every cosmological model, I can draw one of these curves for you. And these curves change as you change the amount of normal matter or the total matter density in the universe, the expansion rate, etc. Okay? So it stands to reason that the day you measure these well, you would start inferring a lot about the universe. And we understand the physics of this very well, so there is no worries that we have misunderstood any of the observations. So let me tell you a couple of things that we can easily read off from this fluctuation in the microwave background, and we have read off. One is, if I look at those power spectra, you see there's a bump and wiggles, right? We understand where they come from. These are basic acoustic physics. Undergraduate students in their labs do that physics with resonant tube experiments, right? So it's not very unfamiliar territory. So one point to remember is very simple, that if there is cold dark matter and ordinary matter, it's only the ordinary matter that interacts with light. It is only that matter that will be present in the ripple, right? So if that matter, you have more of that matter, then the ripple will be stronger. If you have less of that matter, then the ripple will be, not as strong. So this first peak will be higher if the density of normal matter in the universe is high. And even in the, kind of early 80s, it was clear from observations that this was not 10 times this, right? It was already telling you that all the matter in the universe that we see that could be there cannot be all atomic matter or normal matter, right? And this is when Peebles, in his characteristic way, since observations were telling you, essentially ruling out a universe which is totally filled with only baryonic matter that clusters, he said, okay, that means we have to introduce something which clusters under gravity but does not interact with light, right? And there were other ways people had talked about dark matter, but he brought it to the cosmic arena. He said the cosmos has a cold dark matter distribution which is few times the, in fact at this point we know that it's 6 times the density of normal matter. Okay, so this was one big hit, right? The cold dark matter coming in from this point. So this is way back in 82. There's another thing that you can read off from the study of cosmic microwave background from these curves. The location, I was talking about the height of this peak, the location of the first peak in what is the inverse length scale is talked about in terms of something called multipoles. So just remember that this thing at 220 means that the universe is a flat geometry, right? And how do we know that? That's because we know a scale which is inscribed on this surface 43 billion light years away. On this surface 43 billion light years away, I know how big is the 150 megaparsec stick, right? There is a stick of 150 megaparsec. Now, depending on which geometry you are looking at this stick through, whether it is a closed universe or an open universe, spherical universe or a flat universe, the angle here is different, and correspondingly this curve will move to the left or right. So you see the series of curves either moves to the right here or left, right? And if it is exactly flat, then this peak should be at 220. Okay, so these were a couple of things that are amazing. So here too, Peebles, although not directly, had a very strong indirect influence. with Bob Dickey in 79, he wrote a pretty influential article in Einstein's centenary volume, where he pointed out that there are cosmic coincidence. If the universe is not flat, there is a time at which the universe becomes dominated by curvature, which means there's a special time in the universe. And why should it be now? Why wasn't it, a few seconds after the universe was born, or, why is it not, some other time? And as a physicist, as I said, physicists do not like to understand something as initial conditions. You can't say that, oh, this happened because of initial conditions. You want to understand in terms of some rule, right? Not initial condition. And they wrote a pretty strong paper pointing out this cosmic coincidence, which is related to what is called the flatness problem. Unless the universe is absolutely flat, it's very difficult to explain why the universe would be curved, a little bit curved either way, right? And that influenced people to actually look for reasons why the early universe would have a particular scenario called inflation to flatten the universe. Okay, and we somehow, amazingly enough, this was another remarkable point he made, that the universe should be flat, and we found, our measurements told us that it was flat. So let me tell you how good our measurements are. So I started my research when COBE first released its results in 1990, right? And that was a very coarse map of the fluctuation in the microwave background. Then the next decade, there was another satellite which made much, much more refined measurements. And the final decade, we were part of Planck, where we measured this to very high accuracy. And there have been many other experiments. So this plasma screen at 43 billion light years is mapped out to the best details possible, where you have information, okay, at this point by the Planck thing. Now, if I take the Fourier transform of it or create the power spectrum, I get a power spectrum which is absolutely exquisite, right? So just to point to you, this is the power spectrum measured by Planck. These dots that you see have error bars. It's just that the error bars, to see the error bars, you have to subtract out the best fit model out of it. And you see that there's only one model of cosmology that explains all the measurements, right? And that's amazing. And you can resolve not only the first harmonics of this resonant phenomena, but up to the 8th harmonic, but we'll stick to the first peak. Remember, the first peak ought to be at 220 for a flat universe. You read off the value here, it's 220. The first peak needed to be at 74 microkelvin square. That's the value here, right? So this is amazing confirmation that we are in a geometrically flat universe, and we know exactly how much matter density you have, which is also another funny thing, or amazing thing in cosmology, that this is consistent with the Big Bang nucleosynthesis, the concept that all light nuclei were cooked in the early universe, right? This baryon density is consistent with that. Okay. Now, you might wonder, a skeptic might wonder, but you built it all on some resonant phenomena happening on the plasma surface 43 billion light years away. How do you know such a thing is happening? Are you fooling yourself? I would argue that even if I did not know anything about this origin of this curve, right? If I did not know the cosmological theory and work out this curve and the red curve inside it, even if someone just gave me the data and I've just plotted it in an agnostic way, the fact that there are peaks at every regular intervals, like a resonant phenomena, would leap at you. So it's just like, when you look at a crystal and look at the X-ray of a crystal, there are very specific points, right? There is a crystallography done. Similarly, you see that it's amazing that this resonant phenomena is in your face and obvious. Okay? So now going back to the story of the universe. So I told you that the equation that governs the universe on the whole, on large scales, is very simple. Add up the amount of clustering matter, add up the amount of vacuum density or lambda energy density that doesn't cluster, and you had another player called the curvature density. How curved is the universe? And all these three numbers have to add up to 1. Right? I want to convince you that I want you to go back with the idea that actually it is that simple. So what we did was there were 3 players, and from that observation that that peak was at 220, we ruled out, we said that the universe is geometrically flat like this, so the triangles are normal triangles, and you ruled out this part. So you have removed one variable out of this, right? So now there are 2 players playing against each other. How much of clustering matter, how much of non-clustering matter? To understand that, you can do it with the micro background, but another way you do that is to look at how galaxy distribution will evolve from the same fluctuations of the micro background to the current universe if the universe had a cosmological constant plus cold dark matter or just all cold dark matter, right? And starting from the same situation, you would see that they will give you distinctly different structures. To the eye, I'm sure you can see that the distribution of galaxy here is distinguishable from this. We do it very sophisticated manner in terms of correlation functions and many other measures. But to the eye, it's clear that this, if this universe and this universe cannot be the same, cannot be true at the same time, right? And it so turns out that our universe is more like this than this. And this is what Peebles was pointing out way back in 1984, saying that the matter densities does not seem to be larger than 0.3, right? And hence, there must be something else making it up. So now you go back to this, you could have added up everything. So radiation density is anyway 1/100,000th of this, then the curvature density is gone. Now this and this, if this is 0.3, then you are forced to accept that the cosmological constant makes up what 70% of the energy density of the universe, right? Now, when he proposed it, he thought of the cosmological constant. Later, he also talked about broader things like dark energy, but cosmological constant still remains the best bet for this one. So, starting from a very simple framework in which to work, but using physics, you come to amazing conclusions. You realize that most of the universe is made up of stuff that we have not seen in our laboratory yet. We have seen only 5% of the matter that makes up the universe. 6 times that is in the form of matter that does not that clusters, but does not interact with electromagnetic radiation. We don't know what it is, but it is different. And we also see that that's not, as if that wasn't enough. Most of the universe is dominated by energy density that does not even cluster under gravity. It is very strange. But the cosmological constant is something that fits the bill. So here what I'm showing you is this whole process. So you could, instead of going to the Lasker structure, you look at the data from Planck in these green curves. You have all the dials for the cosmological model parameters. How much of cold dark matter to put, how much of baryonic matter to put, what should be the expansion rate, and you vary them, right? And you will find that this predicted curve in black will settle down to the observational curve at only a particular combination of numbers, right? And given that this data is so amazingly accurate, we now are able to pinpoint what the universe is, made up of, right? How much of baryonic matter we know to a percent level accuracy, how much of cold dark matter to a couple of percent, and so on. So we know numbers in cosmology. So it's like you took physics, studied the system, you took observations, measurements, just like any physics subject, and you have accurate measurement of various parameters of the system. Okay, so the story is that after Planck, and so which is why Peebles had such enormous influence on cosmology that people expect him to get a Nobel Prize even in 2006, or when Kobe got it, and various phases he could have got a Nobel Prize. My personal take is he got it once these numbers came out from something like Planck. In 2018, Planck released its final numbers, and this was a spectacular confirmation of a model that he had put forward. He had put in cold dark matter, he had proposed it in 82, 84 he said, oh, there should be also cosmological constant, lambda dominated, and we do find that the best fit model is a geometrically flat lambda CDM model, right, as he had predicted during his career term, right, which is why it's amazing that he got it. But this is the most striking thing, right? He's still looking for something beyond. He doesn't think this is the final story. So this is his post-Nobel interview. He says, I was very uneasy that people were accepting lambda CDM so easily. Because, he felt that he was just fixing the problem to avoid a clash with the data, and again fixing the problem. So it's remarkable that two fixes actually led to a model which is the true model of the universe as far as we can see from observations. So he says, he wasn't comfortable then, he was uneasy then, and he is still startled. And that also shows the humility of this person, right? Normally a person who is kind of regarded as the initiator of a theory, clings to it and says, oh man, I said it and I think that is he is probably the greatest critic of lambda CDM at this point. And, as people will tell you, even in talks that we hear and interact with, he keeps begging, urging people, the younger people, like, generations like ours and later, say, look for holes in the thing. It cannot be this. This cannot be that we have, just had two fixes and the universe has been unraveled. So that's the spirit in which great science happens. So we're getting to summarize the whole thing. So as I said, the main message is the universe is very simple. It can be studied with physics, although we are sitting in this tiny speck of dust in some, galaxy amongst billions. Even with basic physics, we have figured out that 95% of the energy in the universe is an exotic form. There's cold dark matter, there's a cosmological constant or some dark energy. Now what more? Now there are many directions in which cosmology is going. It's not as if we have closed cosmology. It's finally found a base from which you can work on it like any mature discipline in science. So it's the most exciting time to be in cosmology, and particularly I'm addressing the young people. And there are many directions, and some of them, you should listen to talks by young cosmologists in IUCAA. Asim Paranjpe is there, and my host Souradeep, who's disappeared now, but is also there. And you should hear them, and Souradeep in particular, if he's not in Hawaii, he can catch him here, right? And I would like to spend few slides to say that this is obviously not the end of the story, because remember, we looked at the universe as a perturbed system, but we never addressed the question, what perturbed the universe in the first place? And it has to be some very early universe phenomena where these perturbations were generated. And until we nail that, the story is not complete. We have understood the story, but somehow the first chapter has still not been opened to you. You know the rest of the story, right? You know how it evolved from the time that fluctuations in radiation were there to the galaxy formation. So this is the next one of the next frontiers to understand. We understood this part of the universe, starting from fluctuations that we saw on this plasma screen 43 billion light years away, to understanding how galaxies formed. This is very well understood now. This has given us all the rich understanding of cosmology. That there's this other leg. Where did these fluctuations, who stretched the drum and who pinged it, who made that sound in the drum? And we believe that is a very, very amazing phenomena of very rapid expansion in the universe. It can happen. We have theories that can create such a situation, or scenarios that can create. That will naturally stretch your space such that if you rapidly expand something, it flattens out. So it flattens out space, and in doing so, very basic quantum mechanics applied to such a stretching universe, rapidly stretching universe, tells you there will be fluctuations created that could be the seed fluctuations that we are seeing in the microwave background. So this is amazing if we were to nail it, and we have gone very far in nailing it. We have seen many aspects of it, except for one thing, that anything that creates these fluctuations that cause galaxies to come up will also create a primordial distribution of gravitational waves. I mean, all of you must have heard of the LIGO discovery of gravitational waves. Those classical waves coming from merger of binaries. These are quantum origin in the early universe. And that's the next goal of cosmology, to search for this. And you need basically something beyond what Planck could do. And you need a next satellite. So I just wanted to tell you that this is a to-do and must-do for cosmology. Almost every space agency I'm aware of is looking for a way to make it happen. In India, we have proposed a mission called ECO, Exploring Cosmic History and Origin, to ISRO from this consortium, which is also one possible way you could try to look at this gravitational waves of quantum origin from the very beginning of the universe. Okay, so this is a very, very ambitious project, but given enough people, all you have to do is, the path is straightforward, but not easy. You have to build a satellite to specifications with the kind of detectors that can get to that sensitivity. All those are in hand. You have to place it in a rocket powerful enough so that it can take you to the second Lagrange point, which is beyond the Earth-Moon system, 150 million kilometers away, or maybe I got it wrong, but anyway. And then it will point away and measure the microwave background. Okay, and so let me ignore this. Yeah. So let me stop here by saying that we have learned a lot from the microwave background itself in the previous ones, cosmology itself. Now, and that has been kind of summed up in this Nobel Prize, the kind of information that we got about the cosmos, confirming the theoretical predictions or musings of a theorist like Jim Peebles as one milestone, and we want to move forward, and maybe India could be the one taking us to the next step. Thank you.
Wait, there are questions.
Thanks very much, Tarun, for an absolutely lucid talk and ending on such a positive note. We're running a little late, so let's see whether there are a few questions from. Are you willing to do questions, right?
Yeah, sure.
Okay, raise your hands, and there are mics floating around where you need to speak in. Yes.
Hello, sir. Sir, I have a very simple question. When we say that the space is expanding, the universe is expanding, it is a space that is expanding, right?
Yeah.
So does that mean even the size of this room is increasing?
No. So that's an interesting point. So anything that is bound by another force, like this room is made up of molecules that are bound by electromagnetic force, which is much stronger than gravity. So that cannot, the expansion is not strong enough to overcome that. Even if something is gravitationally bound, like the Earth is gravitationally bound to the Sun, even the Earth-Sun distance is not increasing because of the expansion of the universe.
But is it getting the force of expansion to it? But is it still getting the force of expansion?
It wants to expand. So in fact, there's a very interesting paper that Professor Vishweshwara gave me. I had the same question when I started my research and asked Professor Vishweshwara. He gave me a paper by Petrosian and Einstein, which was written a year or two after GR, where they looked at a clump in the expanding universe and showed that as long as the clump is unbounded, it will expand. If it's gravitationally bound, if the binding energy is such that it's a bound system, then the expansion is limited. It's actually not there, negligible.
Okay, and the rate of expansion is greater as we go further away, right?
Rate of expansion appears greater. It's expanding at the same amount, but if you're looking at two things which are far away, it's like an elastic string that you put marks on it and stretch it. These two marks will be moving apart at some rate, but the first and the 10th one will be moving apart at 10 times that speed. Yeah. That is what we see.
And can the rate of expansion of the universe be greater than the speed of light?
Yes, in a slightly more relaxed talk, I would have shown you, if you remember that expanding video that I had shown you of points moving away, there were two red shells. So in fact, yes, the universe can expand fast enough such that light is unable to travel in it. So it freezes.
Okay, let's move
Thank
on
you.
to
Thank you,
another
sir.
question.
Thank you.
You've had enough questions. I know it is always feels that we are expanding because we are eating too much, I think. But has nothing to do with this. Anyway, next.
Sir, which Friedman model do you think is correct?
Oh, okay. So that's interesting that you know the name of these models. These are called Friedman-Robertson-Walker-Lemaitre models. And we think it's a geometrically flat one. So what are called, so there's closed universe, open universe, and a flat universe. So we inhabit a flat universe amongst the Friedman.
So regarding the current data, do you think the universe will continue expanding, or will it stop at a certain time and remain, or will it, come back and another Big Bang will happen later?
No, so as our observations, and if our basic simple theory of cosmology is correct, the Friedman-Robertson-Walker model, it will expand forever. It's a very dull future. Things will expand faster and faster, and slowly,
Thank you, sir.
cold death.
Okay, thanks. Next is there.
We're talking about only observable universe, right?
Yes.
We're not talking about the other multiverse, right?
No, I'm not.
Okay.
Actually, it depends on whom you talk to. I am not a particularly great fan of multiverses.
So,
Where?
there is this cosmological constant to which
Sorry, can you? Oh, okay. Sorry. Yeah.
there is this cosmological constant of which Einstein had proposed, and which was actually he said it. He kind of retraced his words back and said that I'm wrong about it. But other findings of this dark energy, which we are saying that must be the reason why the universe is expanding. Do the calculations and findings, do they corroborate with the Einstein cosmological constant?
Yes. Actually, I mean, again, you would hear different answers from different cosmologists, but I come from the school of thought where, the cosmological constant is enough to explain every observation that we have till date. It's the simplest, in my opinion, explanation for why the universe is expanding at a faster and faster rate.
Sir, is the universe infinite? Means, if we say this much is the universe, what is outside it? We say this much, then again what is outside it?
Yes, so there's a big question. So it's a flat universe, and typically you think of a flat surface, it goes on forever. So that would be the most simplest version. But somehow in mathematics, you also can take a flat universe and fold it up, and it's called topologically non-trivial. Such things are possible. So, but our observation, and this is a serious study. I mean, there are groups in Planck as well as WMAP, who worked to find out if there are any signatures that the universe is closed on itself at a longer scale. The curvature does not tell you that it is infinite. So we have no way to say it's infinite, but we have no observations that it is finite.
We have questions because this program is being live streamed.
Yeah.
And we have questions online as well.
Yeah, so I can ask that question. So the question is from Harshada Gurao. Wouldn't it be more and more difficult to study the cosmos in the future if the universe is expanding at such a fast rate?
Yes, so the lambda CDM model would tell you that there would be things which would be, sort of moving out. There would be a finite distance up to which we will be able to see the universe. And also structure formation stops, so, things don't cluster anymore. It is true, but I mean, I don't think there's any reason to worry about it right now because these are on scales of, tens of billions of years. So it is true that the ever-expanding universe, unless something dramatic happens, and there are people who have models and scenarios where something dramatic happens, and the universe is revived again. But it is heading towards that in our understanding.
Any other questions? Any other mic destination?
Kiran.
No? Okay.
So,
if there are other questions online? No?
So it's already hard enough to detect gravitational waves from very massive bodies and accelerating at very high speeds with the current technology. So if we go to very low masses like the atomic masses and already the massive bodies are close to the speed of light. So why are we still hopeful of detecting the gravitational waves from such subatomic?
It's not, I mean, the question or doubt is very valid, but we are not detecting gravitational waves from atomic objects. We are detecting gravitational waves when the universe was a size of, very small size. But we are detecting gravitational waves from an extremely violent phenomena of inflation, which is stretching out, space in that kind of rapid fashion. Huge amount of energy density was lost into gravitational waves. So it's not as if the gravitational waves are weak. So in terms of delta L over L that you keep talking about, okay, so there we are talking about 10 to the minus 21. Here we are hunting for 10 to the minus 8. So it's a very strong signal, but on cosmic scales. That's all.
Hello, sir.
One more. Okay.
Hello.
Sorry.
Yeah, it's the question is regarding, as you said, one of the slide that a universe is expanding and it's inflating basically. Okay. So and each galaxy is moving away from other. It's like that. So, but I have heard or I have seen a lot of material that there is Andromeda that is neighbor for us.
Yes.
So how is that collision or the merger is happening if they are moving from each other?
So this goes back to the question he asked. See, Andromeda and our galaxy are gravitationally coupled, tied to each other. So they are not free. That's not the scale on which expansion of the universe is happening to its full. So Andromeda is in fact, gravitationally bound to us, and we are going to spiral around each other and collapse. So those are beautiful pictures you must have seen. And this is happening everywhere in the universe. So there are beautiful pictures where you see two galaxies which are plowed into each other. There are clusters which are plowed into each other. So those things are happening. But remember, the scale of the universe is huge. I was talking about hundreds and hundreds of millions of light years size, right? And on those scales, there's an expansion of the universe. But on small scales, gravitation can hold things together.
Yeah, it's fair to say that Andromeda would have collided with us much earlier if the universe was not expanding.
Oh yes, that is also true.
Right, okay, so let's thank Tarun for this amazing evening.
Thank you.
And thank you for asking such very good questions. The Science Day is not over yet. There are night sky viewing exercises will still happen. No? Is it cloudy? If it's cloudy, please go home and come back tomorrow. But we'll see. Go check, please, and see whether there are stars visible. And of course, Tarun showed that if you go to Ladakh, you can see the sky in much better glory.